Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The year was 1911. The intellectual landscape, particularly within the realm of physics, was undergoing a profound transformation. The prevailing model of the atom, the plum pudding model, proposed by J.J. Thomson, the very man who discovered the electron, envisioned a positively charged sphere with electrons, like plums, dispersed throughout. This model, while accounting for the neutrality of atoms, struggled to explain a growing body of experimental evidence, setting the stage for a revolutionary shift in our understanding of the fundamental building blocks of matter. The stage was set for Ernest Rutherford. Rutherford, a New Zealander by birth and a titan of experimental physics, was no stranger to groundbreaking discoveries. He, along with Frederick Soddy, had previously elucidated the phenomenon of radioactivity, convincingly demonstrating that radioactive decay involved the transmutation of one element into another, a finding that shattered the centuries-old alchemical dream and revolutionized chemistry. His work, however, transcended mere observation. He strived to decipher the internal structure of the atom itself, seeking to expose its concealed architecture, to probe its very constitution. The genesis of Rutherford's seminal work, published in 1911, was deeply rooted in the meticulous experiments conducted by his research team, particularly Hans Geiger and Ernest Marsden, at the University of Manchester. They were tasked with investigating the scattering of alpha particles, positively charged particles emitted by radioactive substances, when they were directed at a thin gold foil. The prevailing expectation, consistent with Thomson's plum pudding model, was that these alpha particles would be deflected only slightly, if at all, as they passed through the gold foil. The positive charge of the atom was thought to be too diffuse to exert a significant force on these energetic projectiles. The experimental setup was elegant in its simplicity. A source of alpha particles, typically radium, was placed within a lead block with a small opening. This allowed a narrow beam of alpha particles to impinge on a thin foil of gold. A zinc sulfide screen, which scintillated when struck by alpha particles, was placed around the gold foil. By observing the flashes of light produced on the screen, Geiger and Marsden could determine the angles through which the alpha particles were scattered. To their astonishment, the experimental results defied expectations. While the vast majority of alpha particles passed through the gold foil with minimal deflection, a small but significant fraction was scattered at large angles. Some were even deflected almost directly backwards. This was akin to firing a cannonball at a sheet of tissue paper and having the cannonball rebound. It was quite the most incredible event that has ever happened to me in my life. Rutherford is reputed to have said, "It was almost as if you fired a 50-inch shell at a piece of tissue paper, and it came back and hit." These observations demanded a radical rethinking of the atomic model. Rutherford realized that the only way to explain such large angle scattering was to postulate a structure where the positive charge and most of the mass of the atom were concentrated in a tiny central region, which he termed the nucleus. The electrons, he proposed, were orbiting this nucleus, much like planets orbiting the sun. This model, now known as the Rutherford model, utterly dismantled the plum pudding paradigm. The core tenets of Rutherford's model were elegant. The atom consisted of a tiny, dense, positively charged nucleus, occupying a minuscule fraction of the atom's overall volume. The electrons, negatively charged particles, orbited this nucleus, held in orbit by the electrostatic force of attraction. The vast majority of the atom's volume was effectively empty space. To quantify these concepts, Rutherford employed classical mechanics and electrostatics. He treated the alpha particles as charged projectiles interacting with the positively charged nucleus via the Coulomb force. By applying the principles of conservation of energy and momentum, he derived a scattero formula, mathematically relating the scattering angle to the energy of the alpha particles, the charge of the nucleus, and the impact parameter, this latter being the distance of closest approach between the alpha particle and the nucleus. The formula's accuracy was remarkable, agreeing with the experimental results obtained by Geiger and Marsden. The degree of scattering for a given angle related to the nucleus charge, a key insight that provided a novel method to estimate that charge, a foundational property of the elements. The immediate impact of Rutherford's work was profound. It revolutionized our understanding of atomic structure and provided a framework for further investigation. Specifically, it offered a testable model, predicting how alpha particles of a given energy would scatter at different angles. It also laid the groundwork for understanding the properties of individual elements and their interactions. The scientific community was abuzz. Rutherford's model, far from being a complete picture, presented new questions. Why did the electrons remain in orbit and did they radiate electromagnetic energy? How could the model reconcile the observed discrete spectra of elements with the continuous spectrum expected if electrons were spiraling inward. This instability of the orbital electrons posed a significant challenge to the Rutherford model and thus spurred the next generation of innovation. The subsequent use and evolution of Rutherford's atomic model are intimately linked to the development of quantum mechanics. The model itself, as initially proposed, faced internal inconsistencies when assessed through the lens of the classical physics then in widespread use. However, the very problems highlighted by the Rutherford model provided a crucial impetus for the development of quantum theory. Specifically, Niels Bohr, a former student of Rutherford, proposed a groundbreaking theory in 1913 that incorporated the nascent tenets of quantum mechanics to address the shortcomings of Rutherford's planetary atom. Bohr's model postulated that electrons could only occupy certain quantized energy levels, orbiting the nucleus without radiating energy. Transitions between these levels, he argued, would result in the emission or absorption of photons, thus explaining the discrete spectral lines observed in atomic emission and absorption spectra. Bohr's model, therefore, built directly on Rutherford's groundwork while providing the first glimpse of the quantum regime. The ongoing relevance of Rutherford's work extends beyond the realm of atomic physics. The concept of the nucleus, a dense, compact structure at the atom's core, has been integral to the development of nuclear physics. Its findings, including the discovery of the neutron by James Chadwick, a student of Rutherford, solidified the model. Rutherford also pursued the atom's internal makeup. His work, coupled with the discovery of isotopes, forms a foundation for understanding the different forms of an element and their radioactive properties. Radioactivity's applications extend to carbon dating, medical imaging, and a myriad of other scientific and technological applications. The original reception to Rutherford's model was one of both immediate recognition and cautious skepticism. While the experimental evidence supporting the model was compelling, the underlying physics was incomplete. Its apparent contradiction of classical electromagnetism raised fundamental questions. However, the model's success in explaining the large angle scattering of alpha particles and the subsequent advancements, particularly by Bohr, propelled its widespread acceptance within the scientific community. Critiques focused primarily on the model's inherent instability, a problem readily addressed by the advent of quantum mechanics. The direct influences on Rutherford's work were multifaceted. Thomson's plum pudding model set the stage, providing the prevailing framework for the atomic structure, the experimental techniques, and the understanding of radioactivity, particularly the use of alpha particles as probes of matter, were direct contributions of Rutherford's own research. The precision of Geiger and Marsden's experiments was central to the validation of his model. Moreover, the work of Wilhelm Wien and others on canal rays, positively charged particles generated in discharge tubes, provided insights into the nature of positive charge within the atom. Although this area still required Rutherford's innovation to build and the influence of Rutherford's work on subsequent developments is incalculable. Bohr's model, a direct extension of Rutherford's planetary atom, was a seminal contribution to the development of quantum mechanics. The subsequent development of quantum mechanics itself, spearheaded by Werner Heisenberg, Erwin Schrödinger, and others, built upon the foundational principles established by Rutherford and Bohr. The Rutherford model paved the way for advancements in nuclear physics, including the development of nuclear reactors and nuclear medicine. Furthermore, it provided crucial context for understanding the periodic table of elements and the behavior of chemical compounds. The model's impact can be seen in particle physics, where the concept of a nucleus led to the further discovery and analysis of protons, neutrons, and their subatomic constituents. In conclusion, Rutherford's 1911 contribution, born from meticulous experimentation and brilliant insight, fundamentally altered our understanding of the atom. The model, a triumph of experimental and theoretical physics, continues to shape our perception of the physical world. It provided a framework for understanding atomic structure, laid the foundation for nuclear physics, and provided the very impetus for the exploration of quantum theory. The echoes of Rutherford's groundbreaking work are heard resonating across disciplines, inspiring and guiding scientific advancements for generations. His legacy is that of a pioneer, a visionary who, through elegant experiments and a relentless pursuit of truth, revealed the very architecture of matter.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.